Okay, good morning. So let's wrap up chapter 6 today. Let's see. What does this look like? You're college students. If this doesn't look familiar, you need to get out a bit more. Nah, I'm just kidding. Obviously, I understand students have very busy lives, but as somebody just mentioned, this is a speaker. Yes, a loudspeaker. The individual, so this is a loudspeaker box. Okay, this is a loudspeaker box, but in general, we call it a speaker. Technically, the three individual components that you see here are the actual speakers. We call them the drivers. These are the speaker drivers. Okay. And the reason there are three in there is because each one of them has a specific function. Okay. Each one of them, speakers in general, of course, reproduce electrical signals and convert it into sound waves, right? Electrical waves into sound waves. So each one of these speaker drivers has a specific function. Depending on the size, it reproduces a certain band of frequencies. What is this one called? The small one? Anyone? The tweeter, yeah. Unlike the Twitter that we are familiar with, this is the tweeter. How about this one? It's for the bass, yes. Known as the woofer. And this is for the mid-range. Each one of them has a specific function. As the student mentioned, the woofers, the large ones, are used to reproduce the low frequency signals. That is the loud thumping noises or the bass sounds in audio systems or in audio signals, right? The loud explosions in movies or the thumping beats in a song. So this reproduces low frequencies. Tweeter reproduces high frequencies. Okay, and the mid-range is for vocals. Mid-range is for vocals. Okay, there's also a specialized speaker that is separate component typically, which are known as subwoofers, because the lower you go in frequencies, the more power you need to reproduce. You have to actually move the speaker cones. Physically, you have to move the speaker cones to actually recreate the sound waves. Okay, so subwoofers are the frequencies that reproduce frequencies that are even low, which is basically frequencies lower than 200 hertz. And you need like massive subwoofers, like 15-inch or 18-inch speakers, and a lot of power to actually reproduce those. Okay, so there's a purpose to this. Oh, anyone have a subwoofer in your car, by the way? You kids nowadays. I had two when I was a grad student. Cheap ones, got from Walmart and hooked it up myself. But obviously, not during an undergrad. So hopefully one of these days, yes. Huh? All kinds. All kinds. Indian, world music, hip hop. Yeah, it was a long time ago. I gave it all away when I moved to California. I got a new car. So anyway, it was an old car. I purchased at an auction. A friend helped me buy it, and then I, ripped out the carpet and like installed a few things. It was a, different time. So as I was saying, you have three different speaker drivers, but if you look at the back panel of any kind of loudspeaker, you would only see this. You will see two connectors. That's it. And one cable going into the two connectors. Okay. plus and minus, obviously. If you look at the speakers that are installed here, you can't, I guess they're embedded inside the walls. We can't see them, but there's only one cable going in there. Yeah, there's only one cable with a plus and a minus, 2 wires. Yet, we have 3 speakers, and each one of these speakers has a plus and a minus terminal. So if you open up the back, and it doesn't take too much work, there's only 2 screws holding these together. You open it up and you look at it, and you will see it goes to a circuit. And that circuit will have some large inductive coils, some huge capacitors, and a few resistors. And the circuit will actually split up that single input into 3 different outputs. Okay, 3 different outputs. And each one of these outputs goes into the individual speaker drivers. Okay, goes into the individual speaker drivers. Low frequency output goes to the woofer. High frequency output goes to the tweeter, and the mid-range band of frequencies goes into the mid-range reproducer. This circuit is known as a crossover network. Crossover network. Essentially, it is a band pass filter. Okay, it is a band pass, a high pass, and a low pass filter all in one. Okay. Depending on the make and model, the components would either be expensive or it could be really cheap. Any kind of speaker you take, even the ones that you see in this classroom right now, will have a filter circuit inside it. It's very cheap to make a filter. You take a resistor and a capacitor, you can get it done in a few cents. Right? Resistors and capacitors cost like 5-10 cents each. If you make it in bulk, total RC filter will not cost you more than 10 cents. Literally, I've seen in cheap speakers, there's no circuit, no wires, nothing. You would take a resistor and capacitor, and the manufacturers solder them directly on top of the speaker itself. It's an RC filter. At the beginning of this chapter, we studied RC low pass and RC high pass, right? If you take the output across the capacitor, you get a low pass filtering output. If you take the output across a resistor, you get high pass. So if you have a 2-way speaker like these, you simply stick a resistor and a capacitor on it, and you have a filter. Depending on the make and model, again, a crossover network, like the one that is inside most expensive loudspeaker boxes, will have high quality inductors, high quality capacitors, and high quality resistors. Okay. And so this crossover network is a combination of a low pass, high pass, and a band pass filter, which is the application of a resonant circuit. Okay. So let's look at the transfer characteristic. Yeah. Yeah. So this is frequency in hertz. This is V out, or we can say the transfer function. Doesn't really matter. High pass. Low pass. So this is low pass filter. This is a high pass filter. Right? High frequencies are passed, and the low frequencies are passed. If you take 0.707, the cutoff frequencies for each filter, you would have 2 for the entire circuit. If you take individual, right, this is the break frequency or the cutoff frequency for the high pass, and this is the cutoff frequency for the low pass. You combine both of these together, depending on the values of the components, you can design break frequencies to be on either side. And between the two break frequencies, we can state that there is a band of frequencies that are allowed to pass through. Hence, a band pass filter. So a band pass filter is a combination of two different filtering quantities, high pass as well as low pass. Each one of those filtering of filters circuits will have a break frequency or a cutoff frequency. If you have high pass cutoff frequency first and a low pass afterwards, then there's a band of frequencies in the middle that are allowed to pass through. Everything else is considered to be blocked. So this is pass. All of this is blocked. All of this is also considered to be blocked. Okay, so you have a band of frequencies in the middle that is allowed to pass through. And this is the application of a band pass filter. Most filters that we use in everyday life are band pass filters. They pass a very narrow band of frequencies. Real life application would be if you're trying to tune your radio to a particular radio station. 101.7 megahertz, when you tune it, you are setting your filter to filter out everything else except 101.7 megahertz. A very narrow band of frequencies is allowed to pass through. Everything else is blocked. Okay. So the idea is it's not even a band pass. You want a very narrow range of frequencies. Okay. But obviously it's impossible to just allow one frequency to pass through in real life. So it's a narrow band of frequencies. If you ever try to do a manual tuning between your radio stations, and now it's all digital, but back in the day, we used to have manual tuning. And you try to set your radio station. If you ever set it between two frequencies of a radio station, you ever hear two channels coming in at the same time? You ever have that experience? The reason is you're setting the filter between two frequencies, and it's blocking out a little bit of one station, it's blocking out a little bit of the other station, but both of them are actually coming in at the same time. And so that's why you can hear two radio stations at the same time. You can never hear three, obviously, because you're in the middle of the frequency band. Okay. So coming back to our topic, which is the resonance circuit. Electrical resonance is a phenomena that occurs when you have an inductor and a capacitor in the same circuit. And because both of them are energy storage devices, a phenomenon known as electrical resonance occurs. And what happens at those frequencies is that at resonance, voltages and currents that are larger than the source may appear in that circuit. May appear, not always, but it may happen. It's because they're both energy storage devices, but they're both opposites of each other. Because the inductor stores energy, capacitor stores energy. For an AC circuit, you have positive, negative, half cycles. Inductor, energy flows into an inductor in the positive half cycle and flows out in the negative half cycle. Capacitor is exactly the opposite. Capacitor, the energy flows out in the positive half cycle and energy flows in the negative half cycle. So when you have an inductor and a capacitor in the same circuit, the energy flows into an inductor and out, it goes into the capacitor. When the energy flows out of the capacitor, it goes into the inductor. So it bounces back and forth between the two. This is a very important concept. This is also going to be the basis of chapter 7, which is AC power, and lab 8, for those of you taking the lab. Energy flows in and out of the inductor and capacitor locally, bounces like a tennis ball between the two. Okay. Now, if you have a source that is supplying 10 volts, you have stored energy of 5 volts in the inductor and capacitor, you add them up, you get 15 volts, which is larger than the source voltage of 10. Very simplistic explanation, that's essentially what happens. When you have a range of frequencies being applied to a circuit that contains both inductors and capacitors and resistors, RLC circuit, at one particular frequency, the impedance of the inductor and the impedance of the capacitor are exactly equal in magnitude. Okay, they're exactly the same in magnitude, but they're opposite in phase. Impedance of an inductor is plus 90 with respect to its current. Impedance for a capacitor is minus 90 with respect to its current. If they share the exact same current, then they are exactly opposite by 180 degrees. That happens at one single frequency. And that frequency is known as the resonant frequency because the impedance of the inductor and capacitor cancel each other out. And when they cancel each other out, the only impedance left in the circuit is purely resistive R. And hence, the output of that circuit goes to maximum. So at resonant frequency, ZL plus ZC is 0. The only thing left in the circuit is R. Output is maximum. For all other frequencies, greater and lower than F0, the resonant frequency, the output is lower. And so you obtain a characteristic that looks like this. Output is maximum at resonant frequency. And you get characteristic that is typical of a band pass filter. Hence, if you can take a RLC circuit at one particular frequency, it behaves as a band pass filter. That is known as electrical resonance, and that frequency F0 is noted by this equation. F0 is 1 over 2 pi root of LC. Okay, 1 over 2 pi root of LC. If yes. You would, yes. So the question being asked is the goal of running a resonant frequency to run every filter device at its resonant frequency? Be yes and no, depending on the make and model. Like if you're talking about a real life application, money is always a consideration. Okay, so if you use an inductor, you have to spend more money because inductors have resistance. So if you use an inductor in a filter circuit, it becomes very expensive because you need to use very high quality inductors so that the output is not lost in the inductor circuit itself. So typically, instead of using a resonant circuit, they would use simply just a low pass RC filter and a high pass RC filter. So they would use resistors and capacitors for both high pass and low pass, and you combine it together, it becomes a band pass. So it's not always a, it always comes down to money. Always comes down to money. So if you use an inductor in a circuit, it becomes more expensive. So let's go back. So that question, let me to go back here. So if you have, remember these, the characteristic I drew here is two individual filters, right? Two individual filters. So now we have the circuit. If this was a circuit without the inductor, if you just had R and C in the circuit, R and C, if it's a RC circuit, and you take the output across the capacitor, what kind of filtering do we expect? That's the first filter we saw. It's low pass filtering. If you have a RL circuit without the capacitor, if it's just RL, and you take the output across the inductor, you have the high pass filtering. If you combine all of them together, RLC is a band of frequencies in the middle that is allowed to pass through. Okay, so depending on where you take the output, you have a different kind of filtering action: high pass, low pass, and band pass. That is the crossover network. You're combining both filters, RC and RL filters, into one. Okay. And so that would give you a characteristic that looks like that. Oh, sorry. Note that the frequency, break frequency for high pass filter has a lower value than the frequency for a low pass filter. FL and FH refer, the L and H refer to the actual values themselves, right? Frequency F is 0, then it's plus 1, 2, 3, 4, 5. So it's increasing as you move towards the right. So the low pass break frequency is actually higher in absolute value terms. Make sense? Right? So the L and H is not referring to the filtering action. It's referring to the actual value. That's it. Does not have any meaning beyond that. The actual meaning is actually the opposite, as you see here. Which begs the question, if you have high pass here on the left and you have low pass on the right, what happens if you interchange those two? So if the places for FL and FH or the low pass and high pass is interchanged, what do you get? Take a wild guess. No guesses? If this was FB for low pass, and this was FB for high pass, it's a band reject or band stop filter. Okay, so if the break frequencies of the two filtering actions are switched out or switched over, and of course that depends on the values of the components, then you obtain a band reject or a band stop filter. And again, this is a very simplistic explanation, but essentially that's what happens. Okay, you can design a filter depending on your application by choosing the values. So let's go back to the next slide. As I was saying, F0 resonant frequency is when the impedance of the capacitor and the impedance of the inductor cancel each other out. So at F0, ZL and ZC have the same magnitude. So magnitude of ZL is equal to magnitude of ZC, and the impedance or the phase of ZL and phase of ZC is 180 degrees out of phase. Therefore, at F0, ZL plus ZC goes to 0. Remember at the beginning of chapter 5, I pointed out something like this. What was the application I pointed out at the time? Noise cancellation. You take an incoming signal, you flip the phase by 180 degrees, and you add it together to the original signal. The magnitude is the same, the frequency is the same, but the phase is 180 degrees out of phase. It's the exact opposite. Cancels each other out, goes to 0. Kind of same thing. You take an impedance for a capacitor and an inductor at one particular frequency, 180 degrees out of phase, you add it together, it goes to 0. So total ZEQ as seen by the source would be R plus ZL plus ZC. And because it goes to 0, it simply becomes R, purely resistive. Output goes to max. The same thing happens if you connect the circuit in parallel. At resonant frequency, impedance of the inductor and the capacitor have the exact same magnitude, but the exact opposite in phase. Okay, so you again have resonance. You again obtain a max value at resonant frequency. The resonant frequency still has the exact same equation, 1 over 2 pi root of LC. Okay, still the exact same, no difference. There is a term we use to describe the difference between the two frequencies, and that is known as the bandwidth, noted by the letter B. And that is exactly the same for both series and parallel circuits. It's simply the difference between the two break frequencies. Bandwidth is simply the difference between the two frequencies. Okay. FH minus FL. Quality in terms of the components is given here. QS is 2 pi F0 L over R, or RC for series, and then it's flipped for a parallel circuit. Qualitatively, it is described as the ratio of the resonant frequency to the bandwidth. The narrower the band, the higher the quality. The wider the band, the lower the quality. Okay. Again, the whole point for a bandpass filter is to pass just a narrow band of frequencies. That is the most widest use application. If the quality is high, let's say higher than 5, 6, maybe 10 perhaps, then the graph is approximately symmetrical around the resonant frequency. And then the resonant frequency, we can say, is halfway between the bandwidth in F0. And again, that remains the same for parallel as well as series. But that is true only for high quality filters with a very narrow band around the resonant frequency. Okay. Okay, let's take a pause. Let me know if you have any questions. Any questions? Yes. So the question being asked is, what kind of electrical circuit is used to change the phase of the circuit, right? It could be a very simple circuit as a transistor amplifier. A bipolar junction transistor is used for amplification. Just by its very nature of, and again, this goes into electronics, which is a separate course. The transistor itself, when it performs the amplification, flips the phase of the output by 180 degrees. It could be a very simple circuit like that, but there are other complicated circuits also. Yes. Yes. You talk. So the question being asked is, and I'm guessing or I'm assuming here it has to do with the lab data. Yeah. So there's always been a large discrepancy between the calculated values and the observed values in experimental data. And the reason is the equations are not a full approximation. I mean, it's not an accurate representation of the circuits that we're using. Or there might be, if you're using low quality inductors, that might explain it a little bit. Yeah. No, no, it has to do with the values of the components itself. Yeah. Yeah. Okay, so one explanation I want to give about the parallel resonance before we move on is that in parallel resonance, the total ZEQ, of course, is the reciprocal of 1 over ZL, 1 over R, and 1 over ZC, right? So let's just take ZL and ZC. Right? If we just add up ZL and ZC, what do we get? We have ZL times ZC and ZL plus ZC at the top. And then you flip this, you have ZL times ZC and ZL plus ZC in the denominator, which this goes to 0 at resonant frequency. Hence, the combination, the parallel combination of ZL and ZC goes to infinity. Okay, the effective parallel combination of the inductor and capacitor results in an infinite impedance. Yeah. Infinite impedance. Okay. And so effectively they cancel each other out. No current flows through the circuit. The only resistance left in there, effective resistance in there, I mean, effective impedance in there is the resistance R. Okay. Everything goes to the resistor. Nothing is going down the inductor or the capacitor. It's the effective combination. So series resonant circuit at resonant frequency, ZL and ZC effective combination goes to 0. In a parallel circuit, the effective combination of inductor and capacitor goes to infinity. And hence they both work as a bandpass filter. Okay, both work as a bandpass filter. Okay, so let's go into the last topic, which is Bode plots. Okay. So Bode plot, again, developed by H.W. Bode while working for Bell Labs, is a plot of the transfer function, magnitude of the transfer function was a function of frequency. And both scales are compressed. Okay, both scales are compressed. The reason he developed these is because they were trying to plot large variations of data onto a single chart plot. Okay, so what they did was they compressed the x-axis, which plots the frequency. They compressed it by taking the log of the frequency, and they came up with a new unit to quantify the power loss that occurred in telephone lines. Okay, and so that power loss would deal with large variations, right? You would have input power coming at one end of a telephone line, and at the other end of the telephone line, there would be large losses occurring along the way. And so they needed a way to quantify it. And so they came up with a new unit by compressing the data points on the y-axis. Okay, so let's look at both. Frequencies are plotted on the x-axis. So to compress them, they use the log scale. And when you use the log scale, you plot them as either decades or octaves. Octaves is there just for informational purposes. There is a application for those, but for Bode plots, It's mostly just decades. So decades is basically the ratio of two frequencies, and you take the log of these two frequencies, log of the ratio of two frequencies. If the base of the log is 10, then the change between the two frequencies is known as 1 decade. If the base is 2, then it's an octave. Essentially, if the ratio of two frequencies gives you a 1:10 change, it's 1 decade. If it's a 1:2 change, then it's an octave. So for example, a change from 1 to 10, meaning 1 hertz to 10 hertz, is a ratio of 1:10. So that is 1 decade of frequencies. A change from 10 to 100 hertz is again a ratio of 1:10. So going from 10 hertz to 100 hertz is still 1 decade of frequencies. If, as shown in this figure right now, if you go from 500 to 1000, or if you go from 50 to 100, that is a ratio change of 1:2. That is 1 octave of frequencies. So you're compressing the x-axis, excuse me, by using the log. Okay, you're compressing it by taking the log. The y-axis is compressed by coming up with a new unit. Named after? Who do you think it's named after? AT&T Bell Labs? Bell, that should ring a bell. It's a ratio of two powers, input power, output power. And you take log to the base 10, that comes up with a new unit called Bell. Break it up into 10 further parts, apply a unit prefix of deci, which is 1/10, you get 10 decibels. You have a new unit called decibels, or more commonly known as dB, dBs. If you use a high-end audio video receiver, or even normal audio video AVRs nowadays, the volume control, instead of just being linear scales, would have dBs as their units on the front panel. Okay. So 1 dB is 10 times log of P2 to P1, ratio of two powers. In terms of voltages, again, power is V square over R. When you plug in V square into this equation, the 10 is multiplied with 2, and you get 10 times 2, 20 log of V2 to V1, ratio of two voltages. Our transfer function, H of F, is the ratio of two voltages, V out over V in. Hence, if we wish to plot the magnitude of a transfer function in dB, the equation is 20 log H of F, or magnitude of H of F. 20 times the log of the magnitude of H of F. Okay. So you're taking your data, your transfer function data, and you normalize it, and you're compressing it. Okay. You're compressing your data itself. Even before we plot it, our y-axis data are now compressed. Does that make sense? And we get a plot that looks like this. X-axis is in the log scale. So the chart, you plot these frequency values, and the x-axis is compressed. Y-axis, the data points itself are compressed. Hence, the chart y-axis is not compressed. It's the linear scale. Okay. So the x-axis is log scale, y-axis is linear, and hence this chart or this graph is known as a semi-log chart or semi-log graph. As engineers in your own fields, you may have used this perhaps, or at some point you will use it. Yes. Sure. Here. So again, this is known as a semi-log because one axis of the two is in the log scale, the other one is in linear. But in a Bode plot, both axes are compressed. Okay, the frequencies are compressed on the plot itself, whereas the y-axis, the data points, the magnitude of the transfer function is compressed before we plot it. But both of them are compressed nonetheless. And what it does, it allows us to plot a very wide range of data points onto one single chart. And I will explain how. Linear scale, every division is summed up. It's an addition. You start with 0, plus 1, plus 1, plus 1, plus 1. So you got 0, 1, 2, 3, 4, 5, 6, so on and so forth. On a log scale, you multiply. The multiplier is a decade. 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3. Hence the log, right? Hence a log scale. It's multiplied with an exponent. So there is no 0. You have 9 divisions, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you again start with 1, 2, 3, 4, 5, 6, 7, 8, 9. On a linear scale, you go from 0 to 9, but you're adding it up. On a log scale, you're multiplying. So each division that you see here has a multiplier. That multiplier could be anything, depending on the range you need to plot. You can start with 10 raised to 2 if you wish. Let's say if I start with 10 raised to 0, 10 raised to 1, 10 raised to 2, 10 raised to 3, and 10 raised to 4. And my division goes from 1 through 9. So my first division is 1 times 10 raised to 0. So 1 hertz. Second division is 2 times 10 raised to 0. So 2 hertz. 3, 4, 5, 6, 7, 8, 9. And then I begin again at 1. But this time the multiplier is 10 raised to 1. So 1 into 10 raised to 1 gives me 10 hertz. And then it becomes 2 into 10 raised to 1. So 20, 30, 40, 50, 60, 70, up to the next multiplier, which becomes 1 into 10 raised to 2, 100 hertz, 200, 300, 400, until we get to 1000 hertz, then 2000, 3000, 4000, up to 10 kilohertz, 10,000, and then all the way to the end, 100,000. You can have 100,000 data points onto a normal chart. If you plot this on a linear scale, it would be impossible. You would need a chart paper that's like miles long, 100,000 data points. In a log chart, normal standard letter sized paper, you can simply plot everything out. So a large range of values is compressed, and you can plot it onto one single chart. And on the y-axis, you're plotting in decibels, again, which is the log scale, so it's already compressed. And that's how this chart would work. Again, as I said, if you are engineers, I mean, not if you are engineers, so you may have used this before, or you may perhaps use it in the future. If both axes are plotted on the log scale, then it would be a log-log graph. But only one of the axes here is in log scale, so you have a semi-log graph. You can download chart paper. You can download chart paper from the web. You can actually buy this, but now you can just download it and print it out. And it's just known as semi-log graph paper. Semi-log graph paper. Okay. All right, so there's, I have 6 minutes left. There's one thing I want to cover is a question from a student on how to derive the magnitude and the phase of the transfer functions. So typically this is something we don't do, but since the question has come up, I will explain it. Transfer function for a low pass filter is 1 over 1 plus j f over fb, right? Complex number. The magnitude of any complex number from the rectangular, rectangular path, let's say if it's a plus jb, a and b are the sides of a right angle triangle. So magnitude magnitude of A plus JB is given by the hypotenuse of a right angle triangle. So it's A square plus B square, right? So if I was trying to find the magnitude of the transfer function h of f, it would be like this. H of f, you would have magnitude of 1 divided by magnitude of 1 plus j f over fb, where 1 is A and f over fb is b. So if I want to take the magnitude of the denominator, is simply 1 square plus f over fb square in the square root. Hence, 1 over what you see in that equation, 1 over square root of 1 plus f over fb square. Make sense? Phase is tan inverse of b over a, or arctan. Arctan and tan inverse are the same thing. So tan inverse of b over a. So again, if I was trying to find it for the denominator, I would have tan inverse of f over fb divided by 1. Just the denominator. The numerator, so phase of h of f would be the phase angle of 1 and the phase angle of the denominator. The phase angle of 1 is basically, so this is magnitude of 1. And phase angle would be 0, right? But because it's a division, it becomes 0 minus the phase angle of the denominator. And hence, you obtain minus tan inverse of f over fb. Minus arctan f over fb. That's where it comes from. For a high-pass filter, you have an extra term in the numerator, jf over fp. So when you do the tan inverse of of f over fb, you get tan inverse of infinity, 90 degrees, right? 90 degrees right angle triangle, it never converges. So tan inverse of infinity would be 90 degrees. Hence, you obtain 90 in the numerator and minus the denominator, which is exactly the same. So for a high pass filter, you get 90 minus arctan. That's how we obtain the magnitude and the phase for these. This also leads me to explain the magnitude of a transfer function at f over fb becomes, what does it become? What do you get? When f is equal to fb, 1 over root 2. Guess what value is 1 over root 2? 0.707. That's where it comes from. And h of f is, of course, the ratio of output voltage to input voltage. So when the output voltage drops to 70%, that's our cutoff frequency or break frequency. If you insert power in this equation, instead of voltage, if you have power is V squared or R. So 1 over root 2 square becomes half. So at cutoff frequency, voltage or the magnitude of the transfer function drops to 70%, but the power drops to 50%, 1 over 2, 1/2. Hence, these are also known as half power frequencies. Okay, half power frequencies. All right, questions. Let's see, what time is it? Oh, exactly 11. So again, there's always a derivation, there's always an explanation. It just, we don't have enough time to get into everything. That's, if you are interested in learning more, you can stop by my office, or you can take the EE major class as a tech elective if you wish. Anyway, we'll end class here today. And I will see you all on Friday for AC power. I'll be in my office later this afternoon. So if you have questions, please come by.